Hello, class. Welcome to the next part in the Use of R series. I hope you had a good break back from spring break. Hopefully you all are doing well. We're just going to hop straight into it. Today I want us to focus on what we really think of as the driving statistics for a lot of the work that we do in agriculture, which is work with ANOVAs and work with means comparisons. At this point, I'm making the assumption that you've already worked with ANOVAs. You have a brief overview, at least of what they are, how to calculate them by hand. We're going to talk about how to use R to make that process a little bit easier. I'm going to show you some basic overview functions in R. And when you get to your actual work, your actual thesis work, I'm expecting you to be able to apply it all yourself. So let's start at the start. I'm going to import my data set. Good place to start. So I'm going to start by setting my working directory. File.path. And then I have this headache. You can do this a million different ways, but I'm going to do this just for the sake of clarity. Like we said before, you can even import your data set up here as well, right? We're not going to do that for today. The file that I'm looking for is on my desktop. It's in a handful of folders from there. I think that's it. Well, we don't really even need that. Let's see, we'll try that out. Okay. Then we're going to read in data set. We're going to call this JC data equals read.csv. Thank you, RStudio. And this is, we're looking at the full 4-year data set in this class. We're going to look at everything. So this is data r class.csv. And I'm going to make sure that it knows that my headers, oh, close one, that my headers are real. So header equals true. Let's see if this works. Aha, 48 observations, 5 variables. That sounds about right. So you see we have 2017 for these treatments across 3 reps, 2018, 19, and 20. Our full data set for, I think we said these were tomatoes, yields in tons per acre from those treatments over those years. Now, if we go back and look at this, we notice that year is numeric. We want that to be a factor. Same with the rep and plot. So let's change those real quick. JC data plot as dot factor. JC data. Actually, let's make our lives a little easier and do some copy and paste work. And do this for plot, rep, and year. So I'm just copying and pasting, swapping out plot with rep and with year. And don't hesitate to take a second and pause things if you're confused. At this point, we've already done this, right? This is something that should just be a quick refresher, importing your data set, right? All right. I'm assuming you've got this in front of you now. So congrats, you've imported your data set. We're going to hop straight into running an ANOVA. Call this run ANOVA for tomato yield. I don't know. I'm making the assumption that from the instruction-based portion of this class with Dr. Z, you've got a pretty good feel for what an ANOVA is. This fictitious data set comes from a randomized complete block design. And the ANOVA model that I will set up from here represents that. So let's start straight with, let's call this something. We'll call this, I don't know, yield ANOVA 1. AOV. Then the AOV lets us run that ANOVA. We're going to start by naming the trait that we're interested in observing. In this case, for this data set, we only got one, right? That's yield tons per acre. And that equals saying that the yield in tons per acre is a product of our treatment, right? Those soil tilling regimes and use of cover crops, right? A total of 4 treatments. It's a product of year. We got 4 years. And it is a product of the interaction between treatment and get a little star there, and year. Don't forget we have to call out our data set. Data equals JC data. So we click that. Okay, we've got something here. I don't know what any of this is. That's not true, I do. But what we really need to know is the summary of that. Summary, yield, ANOVA 1. You can run that. Okay, so we see the information in here on our console. We see that treatment. We want to check our degrees of freedom, right? If these numbers aren't right, that means something's wrong. And if you're generating an incorrect ANOVA, it's probably a bad sign, right? So take every opportunity that you can to double check, right? Degrees of freedom is what? That's n minus 1. 4 treatments, minus 1 is 3. 4 years, minus 1 is 3. The interaction, 3 times 3 is 9. We see that the single factors, treatment and year, are significant, right? That p-value is less than 0.05. It's very significant, right? And we see that the interaction between treatment and year is also significant. So that's really going to guide a lot of what we do from here. We have to start with that highest order interaction first. And from here, statistically speaking, it's really incorrect to make comparisons of treatment and year individually if that treatment year interaction is significant. So the work that we do from here on out is really going to focus on that treatment year interaction. If you want to skip over this sort of setup here, what you can even do, I'm going to copy and paste this line of code there. I'm going to say summary. Make sure you have the right number of parentheses. Since I added one at the start, got to add one at the end. You can highlight this, click run, and it gives us the same thing, right? So 1 sets us up in our environment with a whole bunch of information, much more than we really need, but good to have on hand anyway. And we can call things from this yield ANOVA 1. Okay, so we're pretty fortunate in that we only have one trait, right? We only are looking at yield in terms of tons per acre. Usually when you're doing thesis level work, you're looking at a suite of traits, right? You're thinking about quality, you're thinking about yield, you might be thinking about things like chlorophyll amount, right? You might be looking at leaf area, you might be looking at flower color. I don't know. You're looking at a lot of things, right? So we can do the same thing with something called a string. And I'm only going to do this one example of the string because I'm not so good at it. ANOVA with string. But using strings can loop through a whole bunch of columns of data really quickly, which is good for us, right? we've talked about why we have our data frames laid out the way we do. With our first sections really talking about the factors that we're looking at, and everything after that last factor, in this case treatment, we're looking at our variables. We're looking at yield. You could look at, like I said before, quality. You could look at flower color, chlorophyll concentrations, nitrogen or nutrient concentrations, whatever you're looking at, right? So whenever we go through this, having a data frame laid out in this sort of format is really going to be make it or break it. And again, this is a perfect, complete data set. There's nothing missing. 38 is 38, right? So you will have to input or impute missing data. And again, talk to your committee about that. All right, ANOVA with a string. So we had a little tangent. I apologize. Let's hop straight into that ANOVA. So let's think about these variables, these phenotypic datas for our tomato as this plant response factor, right? This plant response to these factors, be it treatment or be it year, or in our case, that interaction. And we can label these as such, right? So we can go through and do these all one by one, or if we had more than just one, we could do a string. So let's first set up these response factors. Call this responses. And these responses are really things like, in our case, it's really just one. We've just got yield in tons per acre. In your case, again, you probably have a lot more. So we're going to say column names, COL and AMES. This is retrieving this set of row or column names from a matrix or a data set. Column names, we're pulling from JC data. Okay. And we're going to say from column number 5, 1, 2, 3, 4, 5, mouse over column 5. On through the end, we're going to go loop through everything. Length, column names, JC data. So we can run this to start with, and it's pulling up our responses. And again, we should only see one response show up because it's all we have, just the one. Right? If we had multiple columns of data, it'd pull up a whole suite of these in the responses for the string. Okay. From here, we're going to do the actual ANOVA step. ANOVA results. And this is going to be done as a list. Let's go through actually. List functions to construct this list, right? It's coursing, checking both kinds of our lists. Great. Go down, and now we have everyone's favorite part of this, the for statement. For I in responses, RES, there we go. And I will say, if this is a little bit too much for you right now, we're just going to graze right over strings and not worry about it. So just kind of follow along as we go through, right? So we're on the ANOVA string portion right now, starting right here. AOV, it's that ANOVA underscore F as dot formula. So it's just setting up a formula. Paste. Paste is a base R item. Again, it's just pasting through. I, right? I in responses. Setting up that string treatment for those responses, right? Plus, might as well add everything in here. Year plus treatment by year interaction. We can say ANOVA underscore results I do the AOV for statistics. Okay. L apply returns the list of the same length as X. Again, this is kind of getting into more complicated R. Some of you are probably at this level where all of this makes sense. Some of you may not be. So again, just skip past it if this is a little bit much, but we're almost through. Whoops. ANOVA results, comma, summary. Let's see if I did this right. Okay. So we looped through. Again, this should only spit out one item, which is yield in tons per acre. We see that we have the exact same results going through that loop as we did above. That's good. Just kind of a fun tangent. But we did this all in base R so far, right? We have no items in our library, no packages selected. This part was all just done in base R. So this is just telling us that there are differences, right? We don't know, is one thing significantly higher than another? And more importantly for your thesis, we don't know why, right? But statistics themselves can only get us so far on that. We can also do this with another fun package that I think a lot of people like in the world of agriculture anyway. ANOVA with Agricola. So that's pulling from our library. Actually, you'll have to do, probably at this point, install dot packages. I've already got mine done, which is Agricola. So go ahead and run that. I'm going to skip past that step because I don't want to have that run through. But we're going to select it from our library, Agricola. And we can check here. It's not selected. That's a little bit frustrating. I think I have an issue with where it's pulling from. But I'll take care of that later. For you, it should work when you select library and click run. So let's see, how do we want to do this? Let's set up through Agricola a nice little model. Let's set this up as the interaction model. We'll call it intermod for our interaction model. With is a base R item, evaluating expressions, JC data. Again, pulling that original data set. Interaction between, we've seen a bunch of ways to go through these interactions so far. This is just one more way. You can see that, again, that asterisk, that star. You could see the colons. In this case, I'm just making an interaction. Year, comma, treatment. Notice I've got a parenthesis missing. So then from this interaction model, we're going to set up our ANOVA model. And this is really just to show you that there are a billion ways of doing the same thing, right? AOV, yield, tons per acre, intermod, data equals JC data. Let's see what this gives us. Does this work? Okay. Shows up here. We can click summary and go through into the same thing, but let's continue on and hop into, well, actually might as well. Let's see if this works. Whoops. So it's just showing that interaction, only, or the significance of that interaction. In this case, it's bulking those sets of four together, which might not exactly be what you want to do. So I've, in this case, created a single factor of treatment year, right? And in these treatment year factors, again, we see their significance. Since it's 4 times 4, that's 16. 16 minus 1 is 15. And there you have it. This probably isn't the way that you want to go about that. But for the time being, let's actually roll with this. We have these, we've created effectively a single factor, right? Treatment year. Kind of a fun way to go about it. And this is all fictitious data anyway, so let's keep moving through. What we'll probably end up finding is that even though we're analyzing it this way, we still get a similar enough story. So we're going to make a data set called P. I don't know, I'm lazy. I'm not creative all the time. We're going to do this HSD test. This is really just that Tukey's means comparison test. We're going to do this from the Anovahsd. Anovahsd. We're going to select intermod from there. Group, of course, is true. And then let's do print P. Otherwise, we're just creating a data frame and we don't get to see anything. Okay, so what did we generate? We got to go through, we got a little bit of summaries, summary statistics on our data sets. We got a yield average across replication for our year treatment single factor. So it's showing us these groupings. Of course, that mean, and aha, we've got these letters that tell us differences. I'm assuming in class you've gone over this, but this is really just putting letters to those confidence intervals for our means comparisons, right? If 2020 tilde cover crop has the letter A, it is not significantly different from anything else that has an A in it. That's 2019, 2018, and 2017 tilde cover crop. But it is significantly different from other parts of this, right? It's significantly different from the 2020 no-till with cover crop. It's significantly different from 2017 tilde, and so forth, right? Common letter, not significantly different. No common letter, significantly different. Easy enough. Let's keep going with this. So I want you all to be able to graph, make a graph from this at the end of the day, right? We're trying to apply this to making figures for our thesis projects. So what do we have here? Let's see, we're looking for P, list of 5. You've got a whole bunch of stuff in here, right? And groups, whoops. Let's make a new data set from this data set. Let's call this HSD groups. We're going to call it P groups, right? We just saw where that came from. We're going to pull from here. So let's run that. And now we have a nice, easy data set to look at. So what problems do we have here? Well, one, this column 0 of row names isn't really accessible to us, so we can't really tie this with this. All right. if we want to make a figure, we also probably want to have some error bars in there. And it's going to be difficult to generate some error bars from this. So let's think ahead a little bit. We've done some work before with the PLYR package. So from here, let's see what that sort of list would generate with those means and standard errors, so we can have those error bars available to us. Let's see how it compares to this information that we have here. So let's do run summary stats. All right. We're going to do library PLYR. I'm just going to skip straight through here and click it myself and get past that step. What do we want to call this? Let's call this our stats data frame. Stats df equals ddply. This should look very, very familiar. JC data, that's our data set. We're pulling treatment and year. And we're going to summarize. Okay. N. Oops. Is length, yield, tons per acre. And we're going to copy and paste this and save ourselves a little bit of time. Whoops, forgot my commas. And the last one won't. So we're going to do N as a length. We're going to calculate a mean. We're going to calculate, whoops, let's write these over here. Mean. Clicking's tough. We're going to calculate standard deviation. We're going to calculate standard error. So if you remember these functions, there's some base R stuff. SD. SC is standard error is the only one that we have to kind of compute manually, a little bit less base work, which is a standard deviation divided by the square root of n. I think that should work. And we'll just put stats df. Run. 16 observations, so we've got the data set that we've probably already graphed at this point, right? This should look very, very familiar. Let's close these out. Take a look at stats df compared to HSD groups. We see that they both have 16 observations. Okay, that's a good sign. HSD groups has 2 variables, and stats df, that's from the PLYR package, has a total of 6 variables. So this is set up in a more typical way where column 0 is just 1 through 16. Our HSD groups, we need to fix this if you want to have access to it. But once we fix it, we'll also want to make sure that when we merge together a bunch of these data sets, we can have a common column name. Maybe we'll call that common column name year treatment or something like that. But we see yield in terms of tons per acre. Let's see if we get the same 2020 tilde CC, 52.6. What was that again? Tilde cover crop 2020. Oh, that's no tilde. Tilde cover crop 52.66 repeating. It's probably a good sign. Okay. So we've got two data sets that we want to bring together now. We have this HSD groups, which shows our statistics in it, right? We've got these groupings in a letter format. We want to combine that with the mean and the error bar information. We'll say mean and, I don't know, standard error, doesn't matter, from the stats DF from the PLYR approach data frame. So one of the things that we're going to learn real quick is something called cbind. Let's call this HSD data frame. We'll do DF, so we know that we want to combine these two. Cbind. Let me delete this so we can read through what that is. Cbind. Item of base are, take a sequence of a vector or data frame arguments and combine them by columns or rows respectively. All right. So cbind HSD groups. This is the data frame we're working with. So we're going to start by setting up row names as null HSD degrees of freedom, or the data frame is null. We don't want to do anything with that. We do want to focus on column names. Actually, we'll set this all up first. And then we're going to set these custom column names because why not? We're going to set this as, well, let's run this first. Let's see if this gives us anything useful. Let's run it. We have an error. What did I do wrong? Cbind. Oh, I didn't set row names. Row names. HSD. No, we have 1, 2 brackets there. 1, 2 brackets there. Okay, let's see what HSD DF looks like. Aha! It moved this information over 1. That's extremely valuable to us. So now we have this thing called row names, HSD groups. Great. And we've still got this column 0, which it's fine. So let's set our column names now that we know this works. Column names, we're going to call this first column that's currently set up as row names, HSD groups. We're going to call this year treatment. This will be our common unifying piece of information. And let's set the next one as yield tons per acre. And our final one as, I don't know, group. Let's run all of that. Uh-oh, that's no good. What did I do wrong? Aha, forgot a bracket there. I think I need to get rid of that bracket. Okay, always watch and see where those parentheses or those brackets are at. Really easy to make mistakes based off of that. So now we have something that we kind of like, right? We've got this more traditional setup that we've had before. We have a year treatment combination. We've got groupings and so forth. Okay, so we're a step closer now. Let's see. Let's maybe work from here with the stats DF data frame. Kind of jumping back and forth a little bit, but sometimes that's the way it goes. I see that we have year and treatment in here, but I want a combination called year treatment. So how do we take care of that problem? I want to make new column called year treatment, but I also want to keep treatment and year. This will help us make our plot later. So let's produce a common column. Probably should annotate better. This is making a new column. So we're going to do stats df, and we're going to make a new column in stats df called year treatment. Okay. Now the function we're going to use is called paste. Concatenate vectors after converting to character. That's good. I mean, we recognize the word concatenate probably at this point from Microsoft Excel, right? Just brings this effectively a concatenate function. So we're going to do stats df, and you probably guessed it, year, comma, stats, the other option or item that we're going for, the other column, df treatment. And will this work? Let's find out. Okay, so it worked, it looks like. Let's see what it shows us. We have treatment still, year still, we have year treatment. This is great. Let's see how this looks compared to this file. Now, one thing that I notice here is one has a period in it, the other does not in that year treatment column. So let's go back here and let's use another base R sep, a character string, separate in terms, equals period, right? You know that you can follow almost an identical approach in Microsoft Excel. Let's see if this works. Aha, 2017.notil, 2017 no-till 31.67. No-till 2017 31.67. That's a very good sign that those means align. Okay, so what do we have left? We've got two data frames that have a common column, and I think we just want to go from here to creating a new data frame. We're going to call this new data frame plot data. And this should help lead into your existing ggplot information. Plot data, merge is our base R function, merge two data frames by a common column. That's so convenient. Merge stats df as our first data frame or data set, and our second is hsd df, and we're going to merge it on the basis of year treatment. All right, moment of truth. Does it work? 16 observations of 9. 9 is 7 plus 2. It's a good sign. Let's see what we get. Okay, so we have our year treatment. You've also got with that treatment year. And of course, those all add up. They make sense. 2017 tilde CC, that's a good sign. There are 3 reps. Okay, n equals 3, our length. Does our mean equal yield in tons per acre? Yes, it does. This is convenient. We also have our grouping function. This is our the result of our means comparisons. So now we have a lot of information in a single data frame. So what can you do with this? Well, I just from looking at this know that you can make a bar graph now, just like you could before. And you can make a bar graph with error bars on it. You can set those error bars as standard deviation or standard error. And above those error bars, you can put that grouping, that means comparison letter. Now, I'm debating right now whether I want to do that with y'all or if I want you to do that separately. I think my goal is for y'all to do that separately, but I'm going to make a separate video, a second video that will show me making it from this step, but I really want you to attempt to make this on your own. In my experience, some of the best strategies for learning some of these functions in R is just give it a couple of shots on your own. So I'm going to stop the video here. From here, I'm going to ask you to make a nice figure, and I will look at making one myself.